we're going to talk about polar covalent bonds. We're going to address the concept of resonance. Now, resonance is something that's going to be extremely important in organic chemistry. Mostly going to be talked about actually in the second semester, but we'll talk about a little bit this one as well. Polar covalent bonds, going again way back to general chemistry. In general chemistry, we were taught that if we have a covalent bond, we're sharing electrons. If we have an ionic bond, we are not. Actually, it turns out that these two are limits. Think about a mathematical limit. Here we have perfect sharing and caring, and here we have none. Most compounds, and virtually all carbon compounds, are going to be somewhere in between. And that is the thing that gives carbon compounds the reactivity. Let's consider hydrogen, H2, and hydrogen fluoride, HF. These are both simple diatomic molecules with covalent bonds. If we look at the electrostatic potential map here for hydrogen, remember the electrostatic potential map is going to more or less describe electron distribution. Now in hydrogen, we have two identical atoms. When we do the calculation as to where the electrons are surrounding these two atoms, we would get something like this. Hello, there it comes. So this basically is a calculation that tells us where we would expect to find the electrons. Oh, you put some limits, so 90% of the time. Then the next thing you do is to color this. The coloring is based on electron distribution. And for something like hydrogen, it is just remarkably uniform. Again, we have two identical atoms. An example of perfect sharing. Nice green little ball. If we look at the same exercise here for hydrogen fluoride, however, start off with HF. We're going to calculate the electrostatic potential map and color it. When we do that, we wind up with something very, very different. This is a very nice Easter egg, isn't it? When we do electrostatic potential maps, the convention is blue will represent a positive charge or an electron deficiency. Red represents negative charge or excess electrons. What this is telling us is that this covalent bond here is very, very highly polarized, and that the electrons are being sucked away from this poor little hydrogen, and they're residing here around the fluorine. Once again, most covalent bonds in carbon compounds are going to be polarized, and that is the thing that gives them their reactivity. We refer to this as a dipole. Again, it's just an arrow with a cross at one end. This is the positive end, that's the negative end. You don't have to draw it colored, but it's just cute if you do it that way. The origin of all this, of course, is electronegativity. The reason we have polar covalent bonds is that elements will have different electronegativities. Electronegativity is simply a measure of how that particular element attracts electrons towards itself. Arbitrary scale, fluorine here is the most electronegative at about 4. As you go up, any group tends to increase. As you go across any period, it also increases. That makes for francium down here the lowest, and again, fluorine the highest. This is the simple explanation as to why we have polar covalent bonds, just due to electronegativity differences. All right. Let's apply this to some simple molecules. Water, we're all familiar with water. This is the Lewis structure of water. Oxygen has a valence of 2, so it has 2 covalent bonds, and it has 2 unshared pairs of electrons. The geometry here, the electron pair geometry, is going to be sp cubed or tetrahedral. However, in the valence shell electron pair repulsion, this is called bent for molecular geometry because you only look at atoms. So this is bent geometry. If we replace that with a model here of water, this is what it looks like. Here's our, again, this is tetrahedral, and we have 1, 2, 3, 4 things around it. The geometry, molecular geometry, is referred to as bent. Now, the electronegativity of hydrogen is about 2-ish. Oxygen is 3.5. So that means that oxygen is going to pull the electrons from these covalent bonds towards itself. That gives us 2 little dipoles along these covalent bonds. And that generates what's called a molecular dipole. Basically, that's saying that this end of the molecule is going to be positive, and this end is going to be negative. If we take and calculate an electrostatic potential map for water, we would get something like this. Again, here's our negative end, here's the 2 hydrogens, and these are our positive ends. We can do the same thing here. Here's our dipole. We can do the same thing with an organic molecule. This is methanol. Its functional group of an alcohol. We have a CH3 bonded here to an OH. Once again, if you do electronegativities, carbon is 2.5, oxygen is 3.5, so this bond is going to be highly polarized. Once again, the electrons are sucked from this end of the molecule up towards the oxygen. Here's our electrostatic potential map. Again, you see all the electron density up here. Again, being pulled away from the hydrogens and the carbon. When we do reactivity of alcohols, the functional group alcohols, these electron pairs and this polarized bond here are going to be the thing that gives alcohols their characteristic reactivities. That's why we care about this. There's another way that we can talk about electron distribution in molecules that doesn't even require a computer. And this is the concept of formal charge. In a formal, when you're doing a formal charge, what you're going to do is look at, say, this structural drawing, and you're going to decide where the electrons are. One way to look at this, what if we took this molecule, this again is methanol, and we split it. Here's our double bond, or our the electrons for a single bond. Oxygen is more electronegative than carbon. Therefore, if we split this bond, we're going to give these electrons to the oxygen. And we wind up with this. Come on, there you go. Here's our oxygen. Now has all of these electrons, and the carbon doesn't. Well, if you thought about doing this, this is going to place extra electrons on this oxygen at the expense of the carbon. We started off neutral, we've taken the electron away, and now this must be positive. Oxygen had one electron here, now it has two. It must therefore be negative. Oops. The thing just won't work for me. My battery is dead. So the formal charges here, even without doing the mechanical thing of breaking the bond, we would say that the oxygen is negative and the carbon would be positive in our neutral compound. Now there's a nice simple way to do this using a formula. Okay? The formula is going to be this guy, and you could write this on your 3x5 card if you want. Formal charge. What you're going to do is look at the group number for the particular element. You're going to see how many electrons you have around it. You're going to take half of the bonding electrons, you're going to subtract any unshared electrons, and you're going to get a charge. So let's look at our trivalent carbon here. Carbon is in group 4. We have 2, 4, 6 electrons around it. Take half of those, subtract them. We have no unshared pairs, therefore this carbon is +1. Very simple little formula, very simple exercise. Let's do it on a whole molecule. Oh, hydrogen, okay? Group 1, we have one covalent bond here, so half of 2 electrons, that's 1 minus 1. Hydrogens here are 0. Simple exercise. Let's go ahead and do a real molecule. This is called trimethylamine N oxide. Let's look at the nitrogen and the oxygen and assign charges. I left a little formula down here because I don't remember formulas well either. Nitrogen lives here in group 5, doesn't it? We have 1, 2, 3, 4 covalent bonds, 8 electrons. We're going to subtract half of those. And we don't have any unshared. Group 5, -4. We're left with +1. Our nitrogen has a +1 formal charge.
Why is it 8? Why is that 8?
We have 1, 2, 3, 4 covalent bonds, 8 electrons. Our oxygen, we are in group 6. We have 1 covalent bond, and we have 2, 4, 6 unshared pairs of electrons. Group 6, -1, -6 more. Our oxygen is -1. just for jollies, let's do a couple simple molecules here. This is azide ion, N3 minus 1. Go ahead and do formal charges on all 3 nitrogens. Nitrogen on the end here, group 5. We have 2 covalent bonds, so we're going to subtract 2. We have 4 unshared electrons, subtract 4 more. This is minus 1. The guy in the middle, still group 5. We have 4 covalent bonds, so we're going to subtract 4. And that makes this guy plus 1. And the nitrogen on this end, well, gosh, it's identical to this one, isn't it? So we have minus 1, plus 1, and minus 1. Just to make you feel good, if you add these 3 together, you get minus 1. And that's the charge of azide anion. Now we're going to talk about resonance in just a second. I'm sure you realize that we could take this structure and move one of these electron pairs, and if we did that, we would have a resonance form. Let's do that. And go ahead and take this one. Still azide, and do the formal charges. Yeah, that's the simplest way. Just use the form. Oh,
Or if I don't remember.
any way you can do it. That works for me. All right, our nitrogen on the end here, we have 1 covalent bond, so we're group 5, subtracting 1, and then we're going to subtract 6 more. That makes it minus 2. Little fella in the middle here still has 4 covalent bonds. It still is group 5. Therefore, it is still plus 1. And this guy down here, well, we have 3 covalent bonds. So that's 5 minus 3. And then minus 2 more is 0. And still, if you add them all up, it's minus 1. Just in general here, these are common representations of carbon compounds, nitrogen, oxygen, sulfur, whatever. We will talk about these one at a time as we do it. But if you do the formal charge for a carbon with 3 covalent bonds and 1 unshared electron, you will get that this is a 0. This is called a radical. Again, this only has 7 electrons around it. Very, very reactive. Carbon radicals, again, very reactive species. We'll spend half a chapter talking about them. If we have a carbon with 3 bonds and no unshared pairs, it will have a formal charge of +1. We will call that a carbocation. Carbocations are very important intermediates in many, many reactions. Carbon with 3 bonds and a pair of electrons, formal charge of -1. Carbanion, we call that, again, very reactive intermediate. Nitrogen with 4 things, +1. Nitrogen with 2 things, -1. 3 bonds to oxygen is plus. Same thing with sulfur. Always remember sulfur is just an oxygen wannabe. Okay? 1 bond, -1, 1 bond to sulfur, also -1. So those are basically the ones that you need to remember. Any questions? All right. When we drew our 2 azides, we did resonance, right? Resonance is very, very, okay, this is the same thing I just said. Now we can go. Resonance is a very important concept in organic chemistry. We will use it to rationalize reactivity, and we will use it to predict reactivity. When you talk about resonance in organic chemistry, you must begin with this molecule. This is benzene. Benzene is the one that it was just it was very, very difficult back in the old days because it looks like it's got 3 triple bonds, or got 3 double bonds, but it didn't undergo any of the reactivities that things with double bonds should. So it was just a very peculiar thing. This was solved by a gentleman called Kekulé, organic chemist, as he drank scotch and hallucinated, actually. That's a nice story, but the solution had to do with resonance. So this is what benzene looks like. 6 carbons in a ring. These are all carbon-carbon double bonds alternating with single bonds. Now if we take this and we draw it as a line structure, it would look like this. That's the way you will draw benzene. What Kekulé reasoned was that the reactivity of benzene wasn't that of a typical double bond, because if you took benzene like this and you simply lift the electrons from here to here, up to here, down to here, kind of like this, one more time, then we would get this structure. The double bonds have moved. So Kekulé, in his notion, suggested that actually benzene was madly flipping back and forth. And that's why it wasn't really a double bond. Well, he was wrong. He's still very famous for it, but he was wrong. Benzene isn't madly flipping back and forth. If we think about how these double bonds are put together, each of these carbons has a p orbital left, don't they? All these p orbitals, top and bottom, overlap. And when they do, they form this. This is the electrostatic potential map. And we have this huge pocket of electrons above and below the plane called a pi cloud. So just like we saw for a double bond, benzene is not madly flipping back and forth. It actually just looks like this, but it is resonance stabilized. That is why it is so stable because we have this huge pi system as our bonding mechanism, not really little dashes they can move around. These are just more representations of benzene. Again, our electrostatic potential map. Huge cloud of electrons. We explain the stability of benzene using resonance forms. When we do that, however, we're all very comfortable in the notion that benzene does not look like this, does not look like this. It's simply a series of p orbitals overlapping constantly. When we draw resonance forms, the rules are very simple. Only thing you're allowed to move are electrons, not atoms. They all must be legal Lewis structures. Electrons move only between adjacent sp and sp squared centers and between heteroatoms that are attached to them. And remember, resonance forms, like we draw for benzene, are limits. It doesn't ever look like this or this. It's always the hybrid in between. But we will move electrons, flip them around a lot, because that's how we can predict reactivity and especially points of reactivity. We'll talk about carboxylic acids in just a little bit next week. But that's a classic example also of reactive or resonance stabilization. This is a carbon-oxygen double bond and a single bond. Again, we can move the electrons, make this resonance form. In fact, the hybrid looks like this, with half a negative charge on each oxygen. Any questions? All right, well, the one that's on the test is now benzene. Because organic chemists have kind of cruel senses of humor. The one that's always on the test is this guy. This is called the tropylium cation. Yes, that is a 7-member ring. Now, why would we put something like that on the exam? Because it's just so much fun to watch people try to draw 7-member rings. It really is. Try it. In fact, tropylium is a carbocation, right? But it is a resonance stabilized carbocation. And it is the most stable carbocation that's known. Go ahead and start with tropylium and draw me resonance forms that will explain exactly why this is so stable. Remember, these are all sp squared centers, so we can move electrons between them. Let's just do our first step. I'm going to grab one of these, move it up, and that's a resonance form. Go ahead and draw some more. Seven-member rings really are difficult to draw. And of course, artwork does count. What we've done here is taken this electron pair, moved it in like this, and then has moved our positive charge from the top pair down to this carbon. Now we can do that again. We can grab this electron pair, move it up, and move our positive charge down to here. We can grab this electron pair, move it in, and our positive charge is now here. We can grab this electron pair, move it up, and our positive charge is here. And then here. And then here. Finally, if we do this one more time, we're back where we started. There are 7 identical resonance forms here. Tropylium ion is so stable because the positive charge is spread out evenly on all 7 carbon atoms. Everyone has 1/7 of a positive charge. If you do electrostatic potential map here, it's gorgeous. Here's our resonance hybrid. We do the electrostatic potential map. Gorgeous, gorgeous electron cloud. In chapter 14, I believe, we will realize that in addition to just stabilizing the charge by moving it around, tropylium ion shares with benzene the property of aromaticity. An aromatic compound, just like benzene and tropylium, has an inherent stability because the electrons, the number of pi electrons here, hits certain key limits. And again, just very, very stable. Let's do one more quick problem here. Towards the end of 235, so that's next semester and then some, we will address carbon acids and carbon acidity and the use of carbanions as nucleophiles. Now we'll talk about what all those words mean, but it's all based on simple resonance. Go ahead and take this structure for acetone, say ketone, functional group, and draw me a resonance form. What you're going to do is grab this unshared pair of electrons that's here on the carbon, a negative charge on it, right? And we're going to move it in to make a carbon-carbon double bond. If we did that, that puts too many bonds on this oxygen, or this carbon, so we have to move these guys up here. And we make this, it's called an enolate anion. As I said, this resonance was good because it allows us to do, to predict reactivity. Basically, if you started here with the enolate anion, you would predict that this carbon next to it is going to have a partial negative charge. And therefore, it will react with things. This is 1, 2, 3, 4, 5. This is 2,4-pentane diol. Go ahead and draw a resonance form for this guy. Once again, we're just going to take this pair of electrons, move it in, make a carbon-carbon double bond, move a pair up on the oxygen, and we have this enolate anion. We can do this again. Grab one of these electron pairs, move it in to make our double bond again, move this guy over, and move this guy up. When we do that, we get the other enolate anion. The prediction is, when you have pentane-dione, we expect enhanced reactivity of this carbon due to both of these resonance contributions. That's a very stable carbanion, actually. Any questions? All right, well, we're going to quit here. Again, there is no class on Thursday. I apologize for that, but I have to be out of town. Next Tuesday is our regular lab day, and we are going to do our first lab, recrystallization, and we will watch our safety movie and all of that stuff first. Okay? And then we will finish chapter 2, move into chapter 3, and we'll be on schedule.
So on the syllabus, we're just looking to switch Thursday into
I'm sorry?
So for the syllabus, we're just supposed to switch to
Yeah, I will put a, I'll fix it. But I'm not going to give you another one. I'll just fix it and stick it on whiteboard.
So it means by the lab book for Tuesday, or?
Yes, you need the lab book and goggles for Tuesday.
Homework is part of our group, right? You just decide
Homework?
homework is practice.
You want to work problems? You should work problems.
Okay.
Are you coming out of the book, or
No.
is it going to be like handouts?
Blackboard, right?
It'll be handouts, it'll be stuff. Yeah.
I have an older version.
Oh, yeah, that's fine. Perfectly fine.
I emailed you. I'm gonna be leaving early, like 10 minutes early to get to my
I pooped out by now. So I don't-
Okay. Okay. Thank you.
That's a train.
Yeah.
So what about
There's also a
Tuesdays?
paperback.
What about Tuesdays and Thursdays?
Okay. I've got two things like that. When I looked at syllabus, I thought that Tuesday was lecture and Thursday was lab. That's the way it always has been. This time they changed.
Oh, so we
So
have
this
to
is
have.
our, right, this is our typical lab day. But instead of just,
So
I'm
this,
gonna have to chapter 1. And Thursday, I have to be out of town, so no class. But next Tuesday, we'll do our first lab.
and then Thursday would be
And
lecture.
Thursday is lecture.
So
Oh.
basically, on your syllabus, all you're trying to do is whatever it says for Thursday,
Anything
put
is
that on
fine.
Tuesday, and anything on Thursday, put on, just switch it out
Oh, okay.
for every week.
Okay, thank
I
you.
apologize for that one.
For labs, are we doing lecture, like for the first half in the lab, or just all?
Yeah, we're, on a typical Tuesday, we just come straight in and we'll do that. This time, we have to watch the movie
Okay,
and then,
but ordinarily it's just.
ordinarily, we just go straight to the lab, the other half of the wall, of the room here.
Oh, it's in this room?
Yep, right here.